Hey everybody, this is Alex Merced with another video on data modeling. And in this video, what I want to do is talk about working with hierarchical data. This could be in the form of trees. We'll show you an example first of like just sort of like the data itself. So I often would work with trees if I'm working in like web development. I'm working with like HTML elements or React component trees. But probably the tree that most people are going to be familiar with is, the family tree. So it's actually draw one out. So in this case, let's say we have, we have mom, okay, mom, dad, okay, in this case we may have, me here, depending on how you want to look at the tree, okay. And then from there we have grandma and grandpa. Okay. And you see going for me, my ancestors are my mom and dad, and then even further along, grandma and grandpa. It just depends on how you want to see the tree. Usually you see a family tree in the opposite direction, but I'm just doing it this way because it's just more exemplify of just generally how you would normally visualize a tree data structure. Where you kind of start from like a root node and work your way down. Okay, but the idea here is that you see there's like a hierarchy of relationships that you would want to capture. They're all people, so I may want to capture them in the same table. But how do I kind of exemplify this kind of relationship? Well, there's going to be sort of three approaches we're going to talk about. There's the materialized pattern, the closure pattern, and the adjacency pattern. So first, let's just talk about like, okay, say family. Okay, is the table. We're going to have 1, 2, 3, 4. How many people did we have there? It was 6, 7. Okay, so 6, because it's 4 for the grandparents, and then 2 for the parents, and then 1 for yourself. Okay, so essentially what we have here is, and then we'll say like, I have to actually add a row here for names, so row above. Okay, so ID, name. Okay, and now in the materialized pattern, you could just say, hey, full, you would just do a full path per se. Okay, and let's just say here, me, mom, dad, mom, dad, grandma, mom side, grandma, grandpa, mom side, grandma, dad side, grandpa, dad side. Okay, so there's like our family tree. So theoretically, okay, the path from me to grandpa, okay, this is, so again, in this case, a tree, again, you always start with just sort of one node at the top. So technically I'm the top node of the tree. So essentially going down the tree would take you to your ancestors. So yeah. Okay, so in this case, the path for me to me would just be 1. Okay, because that's basically the path there. From my mom to, from me to my mom would be 1, 2, then 1, 3. Then from grandma mom would be 1, 2 to my mom, then to my grandma on mom's side. Yep. 1, 2, 4. Okay. Nope, I don't want it as a date. So I'll just do this little thing. 1, 2, 4. Okay. And then for grandma, pa, mom, it would be 1, 2, in this case 5. So the idea is that this full path tells you the full sort of path of how they are allocated in the tree. So then I can basically, if I query grandma, I can know all the nodes that are above and below them in the tree. Okay. Grandpa, dad, grandma, dad. Again, this would be 1, 1, 3, 6. Because again, you always start with the top, the root node, and then you travel down the leaves. Okay, because again, these are all just, again, this is the root node, and then these are leaves of that node, and these are leaves of that node. So essentially, from the purpose of, even though, this looks like the opposite or the upside down version of a family tree than you're probably used to, from the point of view of just your typical sort of tree data structure, these are technically the descendant nodes, and these basically, it kind of works in the reverse order because you're starting from a single node at the top. Okay, so in this case it would be 1, 3, 7. Okay, and basically using this really fast for reading because I have all the information I need about the descendants or the ancestors right here. Okay, I can kind of figure out, okay, hey, where did this particular node came from? The problem is when I update, I have to reconstruct these strings. So that means I have to like figure out, okay, which are the nodes in the path? Then I have to reconcatenate a bunch of strings together. So there's a lot of string operations that go in working in this materialized pattern where I'm materializing the full path. So again, generally good for reading, not as good for writes. And again, there's always a trade-off there. Let's show you the closure pattern. So in the closure pattern, you would just have the table of family members. Okay, but then you would have a table of relationships. Okay, and then here you would have, again, the ID for each relationship. And then basically what would happen is you would have sort of the node ID, then the descendant ID, and the depth or relation, we'll say relationship depth, meaning like how many steps removed. So in this case, first we'd start off by listing each node's relationship to itself. So basically ID1 would just be 1, 1, 0, meaning it's 0 steps from me to me. Okay, and then we just kind of keep doing that. So this would just go, let's see, I think this should have the effect that I want. Nope. Okay. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And technically I could just do this and do that. So now I've captured everyone's relationship to themselves. I'm not going to do every possibility, but just so you get the idea. So now I would start doing like the relationship of like mom. Let's say in this case, let's say from mom to me. So this would be relationship number 8. And mom is the node. Or let's say I am the node. And we're talking about my relationship to mom. That would be 1 step removed in the tree. Okay, and then we just kind of go like that. So then I would be like 9. Okay, so then relationship to dad. And again, that's 1 step removed. And I would just keep kind of creating a record for every possibility. So in that case, now what I can do is I can go query, hey, let me get all the descendants of, node 1. And then I can just query, hey, give me all the ones that have sort of node 1 as a descendant here. And since every relationship is being captured and the depth of that relationship is being captured, I should be able to get, it would get every node that's a descendant of me would just be every node. But I could also say, hey, if I want to get my grandparents, I can say, hey, get me the ones who have a depth of 2, right? Because that'd be 2 steps removed from mom and dad to grandparents. So get me all the nodes whose relationship depth equals 2, who is a descendant of 1. Okay? And then that would capture sort of all the grandparents of Alex. So you can do kind of really robust sort of querying here. And then since you're not creating like these strings, so I'm not creating these like hybrid strings here, it's a little bit less intense on the write. So a little bit not as fast as this for reading, but the trade-off's a lot more balanced. Okay, here with the closure pattern. So again, the idea here is you're using a separate table to capture all the relationships between the different nodes. Okay, then there's the adjacency pattern. Okay, in the adjacency pattern, what you do, Control C. Okay. Basically, every node is going to have a parent ID. So who is their parent node? Okay. So in this case, like dad would be the parent node for these two, mom would be the parent node for these two, I would be the parent node for these two, and then I would have no parent node. So we'll say null. Okay, and there you go. You've captured the tree. Okay, I can basically determine that, hey, I am the root node. Okay, these are the nodes in the second layer, and then the nodes that are the leaves of that node, based on who their parent is, and I can reconstruct the tree and understand the tree that way. Um, Again, this is going to be really fast to write because these are pretty. You're just basically putting the parent ID there. But like depending on what you're trying to do, like if I'm trying to figure out, hey, what's the whole path from grandpa to the beginning of the tree? Okay, we'll have to see. Okay, well, I go here, I query grandpa, then I have to go query dad, and then I have to go then query me. Now imagine if that tree is like a depth of like 10 layers. Okay, that's like one query after another query after another query to go work your way all the way back up to the root node. Okay, so this can be sometimes very, very intense on read because basically I can only go up one depending on the kind of query. If I only need to go up one, then this works out really fast. But again, when you get to more complex trees, looking for larger lengths of the tree, this can get very costly on the read. Okay, so again, these are just different ways to sort of model those sort of like tree-like structures um, in your data model. So again, if you want to capture sort of like a family tree, or think of like the DOM in HTML or the React component tree, this is sort of the different ways you can kind of model your data to capture that. So if you guys enjoyed this, make sure again, like, subscribe, leave a comment. I'll see y'all later. Have a great day and enjoy.